All right, let's get right into it. We all know large language models are completely changing the game, especially when it comes to writing code. But what happens when you take that power and apply it to something super specialized, like scientific network simulation? Well, it promises this amazing shortcut to incredible results. But there's a hidden danger, a really nasty one, lurking right under the surface. It's a new kind of error that's so convincing, it can actually poison research without anyone even noticing. Today, we're pulling back the curtain on something called LLM Ware. So, here's our game plan. First, we're going to talk about that powerful temptation of AI-generated code. We're calling it the AI siren song. Then, we'll dive deep and dissect the most common types of errors. After that, we'll explore something called the clean build trap, and you'll see why a successful run can be so incredibly deceiving. From there, we'll actually give you a forensic toolkit so you can audit your own code. And finally, we'll talk about what it really means to be a brilliant researcher in this new age of AI. So let's start with that temptation. Picture this. You're a researcher, and you need to use this tool that's unbelievably powerful, but it's also got a killer learning curve. We're talking about something like the NS3 network simulator. You are literally facing months of grinding through complex C++. Or you could just ask an AI to whip up the code for you in, 30 seconds? I mean, that's an offer that is almost impossible to refuse. And this quote just hits the nail on the head. The source material calls this temptation a siren song. You know, from the myths where the beautiful songs would lure sailors to crash their ships on the rocks. Well, in the world of research, LLM Ware is that song. It whispers in your ear that you can skip all the hard parts, but what it's really doing is steering your entire project straight towards the rocks of bad, scientifically invalid data. Okay, so let's get specific. What exactly is LLMware? It's not just a bug you can find and fix. Oh no, it's way sneakier than that. This is code that looks perfect. It compiles cleanly, it runs without a hitch, and it even spits out beautiful charts and graphs. But, and this is the crucial part, all that output is completely disconnected from reality. The code doesn't respect the laws of physics or the specific way the simulator is built. It's a convincing, well-written piece of fiction. So how in the world do you spot this stuff? Well, LLMware isn't just one type of mistake. It actually shows up in these predictable patterns, or what the source calls artifacts. You can think of them like the fingerprints that the AI accidentally leaves all over the crime scene. Let's break down the most common ones. We're going to go through a kind of most wanted list of three main culprits. First up, we have the version Frankenstein, a monster stitched together from different bits of code from different eras. Second, the procedural trap, which is what happens when the AI just fundamentally misunderstands how time works. And third, we've got phantom type operates, which are basically pure hallucinations that the AI presents to you with total confidence. Okay, let's start with our Frankenstein's monster. This error happens because LLMs have been trained on, a decade's worth of code from all over the internet, forums, tutorials, old projects. They see it all, but they don't have a good sense of which code is from 2012 and which is from today. So what you get is code that mixes and matches things that should never be together. Think of a Wi-Fi setup from 2015 being smashed together with a 5G model from 2023. Grammatically, the code is fine, it compiles, but the consequence is that your research is now what the source calls legacy poisoned. You think you're testing a cutting-edge network, but you're secretly using an ancient, outdated physics model. Your results? Totally invalid. All right, next up is the procedural trap. Now, this one's a little more subtle, but believe me, it is just as destructive. This all comes down to the AI not getting a core concept in simulation, which is, how does time actually pass? You see, in a discrete event simulator like NS3, time doesn't just flow like a river. It jumps from one scheduled event to the next. But an LLM, which is used to writing normal software, will just write a standard for loop to do something like send 1,000 packets. In the simulation world, that entire loop, all 1,000 packets, executes in zero simulation time. This creates what the source calls the teleportation bug. 1,000 packets just magically appear at their destination instantly, and you get these physically impossible results, like 0 millisecond latency from New York to Tokyo. And that brings us to our third artifact, the hallucination. This happens because, at their core, LLMs are just incredibly sophisticated prediction engines. They're trying to predict the next logical word or piece of code. And sometimes, they predict a function name that sounds totally plausible, but it just doesn't exist. So the artifact might be a call to a function like enable global turbo routing. I mean, that sounds real, right? It sounds like something that should exist. Now, best case scenario, this just causes a compile error, and you fix it.
But the real danger is when the LLM also generates the code for that phantom function to make the error go away. Now you're going down a rabbit hole of custom-built, non-standard code that makes it completely impossible for any other researcher to replicate or verify what you've done. And this all leads us to a really, really critical psychological point. The most dangerous moment when you're working with this stuff isn't when the code is broken. It's the moment it finally works. This is what we call the clean build trap. And I know what you're thinking. You're probably asking, okay, so what? It compiles, it runs. Isn't that the goal? And in normal software development, yeah, you're pretty much there. If your website compiles, the login button probably works. But scientific simulation, that is a totally different ballgame. And this right here, this is the heart of the trap. In scientific simulation, a clean build means absolutely nothing about whether your results are correct. All it is a license. A license to start producing perfectly formatted, beautifully structured, completely wrong numbers. It gives you zero guarantees that your data has any connection to reality.
So why is the data so often wrong? Well, part of it is something called the optimism artifact. LLMs tend to generate the absolute simplest version of whatever you ask for. They often forget to include all the messy, complicated parts of the real world. You know, things like signal noise, packet errors, or how people actually move around randomly. What you end up with is a simulation of a perfect world, one that gives you flawless, amazing-looking, and totally incorrect data.
Okay, so we've painted a pretty scary picture. I get it. But the good news is you are not powerless against LLM Ware. The key is you have to shift your entire mindset. You need to stop thinking like a code writer and start thinking like a forensic auditor. And to do that, you need a checklist to hunt for these artifacts. And this slide right here, this is your toolkit. Let's walk through it. First, check your units. An LLM might set a transmission power to 40 because it's thinking in dBm, but the simulator actually expects watts. That's a huge difference in power. Second, check your events. If you see a while loop generating network traffic, that's a massive red flag. That's the teleportation bug we talked about. It should be using the simulator's own scheduler. Third, check the APIs. Are there header files from a bunch of different conflicting versions of NS3? Uh-oh, that's a version Frankenstein. You've got to stick to the documentation for a single version. And finally, use some common sense and check the physics. Is your Wi-Fi simulation getting a 100% success rate at 5 kilometers? Sorry, but that's physically impossible. Your model is way too optimistic. So after all this, what does it mean for the future of research? It means our entire definition of what it means to be a skilled researcher has to change. It's not just about who can write code the fastest anymore. And this right here is the big takeaway. The most valuable researcher in the age of AI is no longer the C++ genius who can build a simulation from scratch in a week. No, it's the critical thinker. The person who can take that AI-generated code and rigorously, methodically verify every single assumption to make sure it matches the real world. The value has shifted from generation to verification.
I just love this analogy from the source material. It's perfect. The AI is this incredible tool, right? A high-powered telescope that lets us see further than ever before. But it's not a perfect tool. And sometimes that amazing new galaxy it's showing you is just a smudge on the lens. Your job, as the scientist, isn't to just blindly trust that image. Your job is to be the one who meticulously cleans the lens. So, as we all move forward in this wild new world of AI-assisted science, this is the one question we have to burn into our brains. The question we have to ask ourselves, our colleagues, and of every paper we read. Before we get all excited about some groundbreaking result that an AI generated in minutes, we have to stop, take a breath, and ask, is this a real scientific breakthrough, or is it just another convincing case of LLM ware? The entire future of valid research really depends on that answer.